Okay, so this video will be just a brief intro into exponential functions, and then we're going to go over the first two things for exponential models, which is interpret and change in exponential models and interpret in time in exponential models. Please excuse the noise. All right, so let's go over the intro first, a little intro into exponential models. So we've seen exponential models and models that grow at a factor of equal intervals. So for example, you could have like y equals 3 to the x. That means that if you start with 1, it's going to triple every other time. So the next when x is 1, it will be 3. When x is 2, it will be 3 to the second power, which will be 9. So it goes 1, 3, 9, and you see that y equals 3 to the x is increasing, is tripling each one that it goes. Y equals 2 to the x, that's going to be double. When x is 0 is at 1. When x is 1 is at 2. X is 2 is going to be at 4. Next one's going to be at 8. It's going to double 4 to 8. And here we have 10 times half to the x. So what happens is you're going to start at 10 and you're going to be halving it each one that you go. So when you put x to 1, it's going down, it's halving it. Okay, so that's what this is showing you here. So you can reach this in real life situations such as population, bacteria, bank accounts. They use this a lot in compound interest in the banking system and in biology, where you're talking about populations and of bacteria and viruses and and stuff like that. So exponential growth is going to start slowly increase, and then it's going to rapidly increase, and the exponential decay slowly decrease. So I'm just going over this brief little intro into exponential functions so you can see how that ties into interpret and change and interpret in time. So we'll look at the following two formulas. When you have exponential growth, you have y equals a times 1 plus r to the x, where a is your initial, the basic formula for exponential growth is y equals a to bx. But for growth, that b becomes 1 plus r, where a is your initial amount and then the r is your growth rate. So, and when we're doing problems, you kind of see what I'm talking about by your growth rate and your decay rate. And here you have exponential decay, y equals a times 1 minus r to the x. A is your initial amount again, and then your r is your decay rate, okay? So, for example, here they have common bacterial growth deals, common exponential growth deals with bacteria, and you have at the end of 1 hour, your bacteria grows. It doubles for each hour, and they want to know how many bacteria will be there after 8 hours. So if you had 1 hour, you will have 2 to the 1, which is just 2. And then after 2 hours, that 2 doubles becomes 4. 3 hours, that 4 doubles becomes 8 bacteria in your petri dish. After 4 hours, that 8 doubles. Double of 8 is 16. So what happens is you're raising 2 to each of those hours when you're doubling it. And so what's going to happen is you're going to start off with 1, and then you go to 2. I mean, after 1 hour, you'll be at 2. At 2 hours, you'll be at 4. And you're going to go up till it just exponentially grows. Another good example is like basketball championships. You start off with 16 teams, and then you get half remaining from the last round, each round from your So in order for the number of teams playing at each round is half of the number that played the previous round. So you start off with 64 teams. After your first round, you're at half of 64, which is 32. After your second round, you're at half of 32, which is 16. Third round, you're at half of 16, 8 teams, 4 teams. And how the function with that would look was you have 64 initially. You're going to start off with 64, and then you're halving it each time. So here's the formula right here. So your function will be 64, and you're halving it each time as you raise it to your round x, okay? So that's just a basic intro. So let's go ahead and do some problems. So I'm gonna do interpreting, this video is gonna just be interpreting change in exponential function and interpreting time in exponential function. So I'll go ahead and start with interpreting change in exponential functions. So let's go. The change part in the exponential function is this part right here. The part that's gonna tell you change is this part that's being raised, okay? So it has the relationship between the elapsed time t in days since Aaron sent the email and the total number of people who received the email, P of t, is multiplied by the following function. So the first thing it says, every day the number of people who receive the email, and we have to say if it grows or shrinks. Now, if this is greater than 1, you're going to say grow. If it's less than 1, then it shrinks. For example, 3 is greater than 1, so I know this is going to grow. If it was a fraction with the top less than the bottom, like 8/9, then I would say shrink, because that is less than 1. That's less than 9/9. If it was like 2/3, that will all be shrink. But in this case, we have 3, so we know this is grows. So we're going to say first, we're going to click over here and click that our function grows. And I'm going to click that right there. And then it wants to know what factor it grows by. The factor is just this b, this part right here that's being raised. So the factor it grows by is 3. So the function is growing by a factor of 3. Let's go to the next question. Okay, this one has percents. If you're going to remember for interpreting change, you always want to look at this B part, okay? So we have T is in days. This is important to note. It said the last time T is in days. So this is going by T is in days, and it's changing by 1.65 every 1 day. And now we have to change that into percents. Change it into percents, you're going to subtract 1.1 from 1.65 and then multiply that by 100. And that's how you get it. Basically, it's really simple. It's like 1.65 minus 1 just leaves me with 0.65. And then I just have to know what that is as a percent, which is just 65. 0.65 times 100, that's 65%. So I know it's growing by 65%. And then since this is greater than 1, it's growing, so I'm going to put added to, okay? Once this is greater than 1, you should just know you should choose grow or added to. So I have 65% added to. If it was less than 1, it will be subtracted from. So to find your percent, you're just going to subtract what's here from 1, or do this minus 1 if it's bigger than 1, and multiply by 100. So let's go to the next question. Here, again, it's asking for the change every year. So I'm going to look right here. So it's changing by a factor of 2. So my factor will be 2. And 2, because 2 is greater than 1, I know it's growing. If your B is greater than 1, it's growing. So first thing you want to always look, is that greater than 1? Grow. If it's less than 1, shrink. If it's greater than 1, add it to. If it's less than 1, subtract it from, okay? So I'm going to say growth, and factor just wants exactly what is here. So grows by 2. And I check. Let's go to my next one. Next one wants me to change my change into percent. So I'm going to look at what's here. It wants my decay rate, so I just have to subtract. This is less than 1, so I know this will be subtracted from. And I'm going to subtract this 0.67 from 1 and multiply by 100 to get my percent. Well, what plus 67 cents is going to give me $1? That's going to be 33 cents. So I know it's 0.33 times 100, which is just 33%. So my year will be 1 minus 0.67, that's 0.33 times 100, that's 33%. So 33%, and I can click down here. This is less than 1, so it's going to be subtracted from. And that's how you do interpret and change. That's how you would do this one right here, interpret and change in exponential numbers. There's a lot of interpret and change. This is only the one that has interpret and change in exponential models, not with manipulation, just interpret and change, and the same year, the years is still the same. It's still same every year, okay? Now we're gonna do interpret in time. So I'm gonna exit from there, and I'm gonna click on interpret in time, and we're gonna do one of these. So let's go ahead and do interpret in time real quick. Sorry about that. So I'm gonna go ahead and do one with you. All right, we'll do some with you. So we have here for time, what you wanna look at for the interpret in time, you wanna look at your denominator of your exponent, and that's going to tell you your time intervals. So this is pretty much the easiest of the March ones. So this is telling me that I started out with initial mass of 320 grams of my chemical, and this is telling me that it's decreasing, and it's decreasing by, I have to subtract this from 1, which will give me, and multiply by 100, which will give me 87.5%. It's decreasing by 87.5%, and I have to look here for my intervals for days. So it's decreasing by 87.5% every 61.4 days. I could check that. So I have when T is 0, I'm just at 320. My initial amount is 320, because if I do 320 times 0.125 to the 0 over 61.4, that's just to the 0, which is anything raised to 0 is just 1. So that just ends up being 320 times 1, which is just 320 for my initial time times 0. Then the next time where I'm going to get a whole number out of this is when I have 61.4. So if I do 61.4 years, then that'll be 320 times 0.125 to the 1, to the 61.4 over 61.4, which is just 1. So it's going to be changing by a factor of 1 every 61.4. So the next one will be 61 plus 4.4 plus another 61.4, which will be 122.8. And 122.8, that'll be 320 times 0.125 to the second power. So it's going to be decreasing by a factor of 0.125 every 61.4 days. Okay, so all you're looking at is your denominator. Next one. This loses 3/7, and I know it's 3/7 that is losing. I'll do 1 minus 4/7, which ends up being 7 over 7 minus 4/7, which ends up being 3/7. And again, for my interpret time, all I'm looking at is what's over here, down here, and it's doing that every 3 years. So for interpret time, it's really simple. You just want to look at your denominator. So this one, I'm multiplying by a factor. The number of people, Yana, is increasing by a factor of 4 every 10.5, and this tells me T is in minutes, so 10.5 minutes. And that's how you do that. So I hope this helps with interpreting. So what we did was interpret and change and interpret in time. And the next video will be constructing exponential models. Hope this helped.